Here again, and today we're looking at the method of heat transfer, which is called the thermal transfer. And we say there are basically three methods of transferring heat in a system. There are three methods of transferring heat. The first one is by conduction, the second one is by convection, and the third one is by radiation. So we're going to look at these three methods by which heat is transferred in our materials or in a system. So we start by demonstrating the conduction. We want to look at the conduction possibility. What materials can support the heat transfer? The materials that can support the heat transfer. So we say there are three methods of heat transfer. We have itemized, thermal transfer, or heat transfer. You can use any of the words, thermal transfer or heat transfer. Number one is conduction. Conduction, which happens in solids. This method of heat transfer takes place in solid. Not all solids, but mostly the ones that can pass on the heat. Okay, like metals. Okay. The second one is convection. The second method of heat transfer is convection. Okay, we're going to explain these three in this concept of this class. And the third one is radiation. So these are the three basic ways by which heat is being transferred in our environment or in our systems or in materials. Okay, so we look at the first one, conduction, and we're going to give the concept. We say this one happens in solids, this one mostly liquid, and convection mostly liquid and gas, and radiation through the vacuum, through the air, and so on and so forth. Okay, so let's take a look at looking at an experiment demonstrating thermal conductors. So first of all, we must know what are thermal conductors, what are good conductors. Good thermal conductors, they're usually solids which easily can transfer heat from one part of itself to another part. You heat one part, the heat can spread to other parts of itself. A good example is a metal pan. You take a metal pan or a ceramic teacup. So either of these, the heat can pass from the bottom of it to the other part of the body of the material. So, and then a bad thermal conductor, which we usually call insulator, they are solids which do not transfer heat very well. They do not do this very well. They probably do it a little bit, but they call bad conductors. They call bad conductors. They don't do it properly. They don't do it very well. So they either do it a little bit or not do it at all. So these materials are called bad thermal conductors, or what you call poor conductors, or what you can also call insulators. Is that okay? So, for example, we have a woolly blanket. Is an insulator or a bad thermal conductor, and then also layers of cardboard or paper. So if we come here, we look at conductor as our next topic. So we say we have good conductors, we have bad conductors, good thermal conductors and poor or bad thermal conductors. So we start with conduction. We explain the process whereby the heat energy is being transferred from one atom of the material of the solid to the next one through vibrations. Okay, so the atoms, if you have a material, the atoms in this material, they are closely put together. We know this. We studied this in the earlier chemistry, in where we were doing matters, state of matter. Okay, so the atoms are closely related, right? Closely put together. So when you heat it, the atoms pass the heat energy from one atom to another through vibration. So they pass the heat energy to one another. The atoms do not actually move, but the electrons do move. The electrons are delocalized. They are able to move from one place to another, but the atom itself remain in its position. So the heat from the bottom, if you supply heat from here, the heat from the bottom will automatically find its way. Okay, let's say you use a tripod stand. Let's say you're using a tripod stand. Okay, the heat from this bottom we find its way to the top by this atom pass to this 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 pass to this. So like that. So eventually the one at the bottom we pass the heat energy to from one atom to another till it spreads every part of it. That's why when you use a metal spoon, whether it's a silver spoon or any metal spoon, then what you have is you see that the spoon gradually becomes hot. The handle, because it's all metal, gradually become hot. So the heat has been passed on from the point of contact where the metal itself came in contact with the heat to the other part, which is the handle. The heat gradually spreads to every part of the metal. Okay, so this is for this. Now let's comparing the conductor or conduction in ties and in textile. Like the ties in your house and the textile, like any other textile material. Okay, so we want to see the level of conductions that we have in each of them or both of them, comparing both of them. Now, this demonstration shows why homes use rugs and carpet. Why we use rugs and carpet. You see that the tiles, because they're ceramic, they conduct heats. So we sometimes we use carpet, even when we have tiles, to warm, to make sure that the house is not too hot. In hot countries, so it's better to use rugs and carpet. In cold countries, then it's better to use tiles, because these tiles, they conduct heat. Okay, so now let's take a look at what happens. They find a tile and a stow area of floor. Okay, now in the same room, leave a rug or a bath towel, not a very thin cloth. It must be a little bit thick so that you will be able to feel the difference. Not the one you put on the tiles. It will still look as if you're standing on the tile. So the one that is a little bit thick, that you can feel the difference. Okay, so the textile must stay in the place on the floor for several hours to ensure that they both have thermal equilibrium. So that we ensure the heat, equivalent heat in the tiles of the house is passed onto this what material that you've put on the tiles. So we see that they have both thermal equilibrium. So you have to leave it for several hours before you come and do this experiment. So you stand with a barefoot or your hand. You can use your hands. Okay. Then you place one of the foot on the thighs and or the stone. Either you use a stone floor or tile floors. You put one of your foot on it, and then the other foot on the towel or the textile that you're using. Then you do your observation. Observe the apparent temperature of the two materials as felt through your feet. So you're going to tell what temperature you think you have here, and then the one you have on the one on the floor and the one on the material. So you're going to see that they're different, that the temperature is different. So it will feel as though the thighs are cold while the rug is warm. That's what you're going to feel. It will feel as if the thighs are cold while the rug is warm. However, they are at exactly the same temperature. Both of them are at the same temperature. So what does this have to tell us? And what is happening? Now you see, this is the heat energy is easily conducted by the thighs. Heat energy is easily conducted by the thighs. Now the rug insulates the foot, so it feels warm. The rug is insulating your foot. That's why it's feeling warm. But your foot can easily transfer heat energy to the thighs, so it will feel cold. It will feel cold. Now here is the explanation for this. Thighs and stones are good conductors of heat. Yes, because they are ceramic. Thighs and stones, they are what? Good conductors of heat. So when the foot touches the thighs, heat is transferred away from the foot, making it feel cold. So whenever you can see with the arrow, heat is transferred away from the foot to the thighs. So once heat leaves a surface, then the surface will feel cold. Just like in evaporation. Remember when evaporation takes place, cooling, it causes cooling. It causes cooling because the particles with the highest average kinetic energy, when they escape, then the ones remaining will have a drop in temperature. We have a drop in temperature, and then those ones will cause cooling to take place. So once heat is transferred from your foot to the thighs, then your leg will start to feel cold. Okay? But on the other hand, the ones on the rug or the textile, heat is an insulator. It does not allow heat to go through it. So the foot from here is not able to transfer heat energy to the material. Hence, all the heat will be fed back in your leg, and then you feel a bit warm. You feel warm. So that's for textile, for ties, and then for textiles such as the rug or any good insulator. This is what you're going to feel. They're poor conductors, so they don't allow heat to go through. So this is what you have. Where the foot touches the rug, heat is not transferred away from the foot. This foot feels relatively warm than the one which has lost the heat to the thighs. The one that has lost the heat to the thighs feels cold, and this one feels warm because it's not able to lose the heat. Now the foot has stayed at its own static temperature, so that's why you're feeling it a little bit. Okay, now let's take a look at comparing the conduction in wood and paper. In wood, because this method is conduction, we've used the textile and the ties to do conduction experiment. Now let's take a look at wood and paper. Okay, comparing conduction in wood and paper. A cylindrical, you know the shape of a cylinder, right? So a cylindrical rod made of half wood and the other half is metal is wrapped tightly in paper. So we wrap it in paper, with paper, right? We use paper to wrap them, okay? And then we're going to see it's tightly wrapped in paper, so, okay? Tapped in place. So you can use sellotape to hold the paper so that it doesn't fall off. Okay, now we're going to supply some heat, right? Then let's see what happens. We say hold above cool burning flame and rotate. Okay, we're going to be rotating the wood. We're going to be rotating this wood. We will rotate it, but we will supply a burning flame to it. We supply heat to it. Okay, and then we see what result we're going to get. We're going to see what result we're going to get when we supply the heat. Here are our observations and our results. You say, using a gentle flame, you're going to use a gentle flame. This is an experiment, hope you know that. So this can help you in paper 6. Using a gentle flame and holding a rod clear of top of the flame, gently heat the paper at the joint of the wood and the material. So you're going to supply the heat just at the joint between the junction between the wood and the metal. The junction, that's the joint. Here is where you're going to supply. Under here, this is where you're going to supply the heat. Under here, this is where we're going to supply the heat, and we see how the heat spreads to both sides, the wood side and the metal side. We're going to see how the heat spreads to both the wood sides and the metal side. We're going to see which one can conduct. The whole essence is to find out which of the material can conduct heat clearly. Okay? So we're going to supply this heat at the joint. This joint, this is the center, the joint between the metal and the wood. So that's where we're going to supply the heat. Now, turn the rod so that the paper is well heated and all around the circumference of the rod. Okay, so we're going to be turning this. We're going to be rotating this. We're going to be rotating it to ensure that this paper, we don't touch it so that the paper doesn't catch fire, doesn't start burning. So we begin to rotate this material. We rotate it so that the heat is given to every part in a circular form. Okay, we rotate it so the heat is given to every part of the circumference of this cylinder. We rotate it such that the heat is given to every part of the circumference of this cylinder. Then after that, we watch out for what we get, the outcome, what it's going to be like. Okay, so we stop when the paper is clearly discolored. We stop when we see that the paper has been discolored. Now you remove the rod from the flame and gently unwrap the paper. I observe the burn pattern. Now, a distinct pattern is seen. You're going to see a distinct pattern. Okay, you're going to see a distinct pattern. Now, where the paper touch the metal surface it is undamaged. Where the paper touch the metal, it is undamaged. Where the paper touch the wood surface, it is charred. It's a bit like as if it's ruffled. It's charred. Okay, so see the wood side and the metal side. See the wood side and the metal side. So what happens? Let's see the explanation to what happened. Metal is a good conductor of heat. Metal is a good conductor of heat, so nothing happens to it. Where the paper touched the metal, heat was transferred from the paper into the metal and along the length of the metal. So heat was transferred to the metal and everywhere in the metal. Now this prevented the paper getting hot. So the heat has been transferred to the metal, so the paper on that part was not hot. Now the wood is a good insulator. It's not a good conductor. It's a good insulator. So meaning it's a poor conductor of heat. So when something is a good insulator, it means that material is a poor conductor of heat. So where the paper touched the wood, heat was not transferred from the paper. Heat was never transferred from the paper to the wood. Now this meant that the paper did get hot enough to start to burn. This means that the paper did get hot enough to start to burn. So on the wood side, the paper will burn, right? The paper will get enough heat to start to burn. But on the metal side, all the heat has been transferred to the metal. All the heat on the paper has been transferred to the metal. But on the wood side, the paper couldn't transfer the heat to the wood. So the paper will get heated up itself and start to burn. Now let's take a look at another experiment in conduction. Excuse me. demonstrated different rates of thermal conduction in metal. Different rates of, so we're going to take different metal, we're going to hold them, and we're going to heat them up and see the different rates of conduction. So this experiment is just to find the different rates of conductions in different metals. So here you see we take, if you look at inside here, you can see 4. 1, 2, excuse me. You can see one metal, another one, another one, another one. You can see we have 4 metals. They are held together in this round one. Okay? This one here, inside this round one, I'm not talking about the round one, we have a cross. Okay, this cross here is aluminum. And here, this one is copper. And then this one to this way is iron. And this one to this way is brass. Okay, so these are the 4: brass, iron, copper, and aluminum. Then we have what we call a conduction ring. This is a ring. You can see a conduction ring, something that can conduct heat has been put here. Okay, so we hold them with a stand. It could be a tripod stand or any stand with a lift. Okay, we hold them, and then we're going to supply heat with this. And then we have what we call at the end ball bearings. Okay, to hold this one, ball bearings to stick the different metals to this conduction ring. You see, there's a ring here, ball bearing everywhere, holding the different metals to the ring, to the conduction ring. So this is an experimental setup, and the above apparatus consists of 4 different metal strips of equal width and length. You must cut them to be equal: the aluminum, the copper, the brass, and the iron. We must have them to have same size, same width, and same length, so that we ensure fairness in the experiment, so that we avoid experimental error. The reason why they have to be same size is to reduce error in your experiment. Okay, so that you'll be just in doing what you're doing, so that you can be able to conclude what happens to each of the metals, because we want to find the rate of conduction in each of the metals. Even if the metals, each metal do not conduct exactly the same way from another one. So different metals conduct differently. They have different rates of heat transfer. Okay, so that's what this experiment is trying to show to us, try to demonstrate to us. Now, the ball bearings can be stuck to each of the strips, the metal strips, and we place them at equal distance from the center, using a small amount of wax. We use a small amount of wax to ensure that they all have the same distance from the center. Remember, here is the center. They all have same amount of distance. Then we say the strips should then be turned upside down. The metal strip, after you fixed it, then it should be turned upside down, and then the sets are heated gently using a candle. So we heat the center gently using a candle and see what is going to happen, so that each of the strip is heated at the point where they meet. So the heat is supplied at the point where they meet. It's not like you heat one metal, the other one is not getting the heat. So you heat a center where they meet. Remember, when we are doing conduction, checking conductions in different materials, we always hit the point where they meet. That's what we did for wood and this day just now a while ago. Wood and metal. The point where they meet, that's where we supply the heat, and see how the heat is going to be transferred, or the rate at which it will be transferred to any part or every part of the different metals that we have provided, right?
Yes.
Okay. Okay, so we say when the heat is conducted along to the ball bearings, the wax will melt. So when the heat is conducted, we say when the heat is conducted, that when the heat starts to pass through each of the metal, okay, because you supply the heat at the center here, this heat will travel to each of the metal strip, through the metal strip, okay, to the end. You know, it will start from here and journey to the end, because it's a conducting material. The heat will pass from the beginning, where the source, where the heat is coming from this center, to every side of each of the metal. Okay, but at different rate, because different metals conduct differently. So they will not move at the same rate, because you are not using the same material. You are not using, even if you cut them at the same distance, you cut them to have the same length, the same width, okay, the same distance from the center, but they will not travel, the heat will not travel at the same rate. Why? Because they are different materials. They are different metals. They are different metals. Okay, so their conductivity is different. Their conductivity is different. Their conductivity is different. Is that okay? Okay, so we say when the heat is conducted along the ball bearings, the wax will melt and the ball bearing will drop. The wax with which you used to stick this ball bearing to the you know, you use wax, you use a candle wax. The wax with which you used to stick the ball bearings to each of the metal will melt. Now the ball bearing will drop. Now the question is, which one drops first? The one that drops first has a higher rate of heat transfer. That metal has a higher rate of heat transfer, meaning heat is what is the one whose heat quickly got to the ball bearing first. Is the one whose heat quickly got to the ball bearing first. So it means that metal is the one that has a higher rate of heat transfer than the other metals. Is that okay? Is that okay? Okay, so by timing, you have to use maybe probably a stopwatch, or you have to time them. You have to time them. So by timing how long this takes for each of the strip, then their relative thermal conductivity can be determined. Their relative thermal conductivity can be determined. Is that okay? Because we're going to time how long it takes for the heat to travel to each one. So you time this one, you record the time it takes for that of the aluminum to drop, the time it takes for that of the copper to drop, the ball bearing that is holding that is stick to the copper, the time it takes for it to drop, because the candle wax that was used to stick it to the copper has melted. And then also you take the time it takes for the ball bearings that is holding the iron to drop, because the candle wax that is sticking it to the iron has melted. Then you also measure the time it takes for that of the brass to drop. So at the end of the day, we know their time, and once we know this, we'll be able to determine their metal conductivity, which one conducts the highest, okay, among the three, and so on and so forth. Is that okay?
Yeah.
Now this is between a glass and a copper. Okay, this is where they meet, and then we watch and see what's going to happen.
Okay, so here's a question for us to consider. And let's start by reading through the question to get a better understanding of what is required of us. The composite rod shown in the diagram below has 4 push pins, or thumbtacks, or drawing pins, attached to it with wax. If the rod is heated in the middle, which pin will fall off first? Explain your answer. So let's just have a quick look at the diagram here. I've got a source of heat, in this case a Bunsen burner, and it's heating up this rod. Rod's made of 2 different types of materials.
Okay, I guess we saw that, right? Did we see that? Did you see that? Yeah, it was just to find out which one we drop first. Okay, of course the first one on the metal side, the first rod on the metal side will drop first, because the heat will travel. We get to it first, right? So that's the one that I will drop first. Okay, so that's that for that. Let's go to the next one. So still on thermal conduction, now we are going to thermal conduction in solid. Now we want to explain the what is happening when you take a solid and you heat it. When you take a solid and you heat it, we want to explain what is happening in it. Now, let's say we say conduction is the main method of thermal energy transfer in solids. So conduction is the main method by which energy is being transferred in solids. Is that okay? So when you take a solid, heat is being transferred in solid by process of conduction. Heat is transferred mostly in solid by a process of conduction. Now, this will happen, conduction usually happens when two solids of different temperature come in contact with one another. Two solids of different temperature come in contact with one another. The one with the higher temperature will transfer the heat energy to the one with the lower temperature. That's the hot one will transfer its heat to the one with the cold one. Okay? Or you take one same solid, you heat one side, you supply heat at one end, and the other end is cold. Then we're going to see how the heat that is supplied from one end is going to travel to the other end. We're going to see how the heat, the thermal energy, which is the heat that you're supplying, how it's going to travel from one end of the metal to the other end, the cold side of the metal. So the one that you supply the heat, the part of the metal where you're supplying the heat is the hot part. And then the other part, the other end is the cold part. So we supply heat to one end, then that end becomes the hot part, and we're going to find out how the heat, this heat, gets to every other part of the metal, especially to the cold end, the other cold extreme end of the metal, like you see, as you see in this diagram. So we have a metal. You can see this metal. These are the atoms. Okay. Do you see the atoms are only vibrating? You can see the arrow in them is both sides, meaning they don't move. They only vibrating. Then you see the dark one that has only one arrow. This one is the electrons. It means the electrons are able to move from place to place. The delocalized electrons are able to move, and they can hit the atoms and bounce off like that. They're able to move. But the atoms are only vibrating in a fixed position. These atoms are only vibrating in a fixed position. So when two solids of different temperature, like this one, the hot temperature, this side, because you're heating it from this side. So you can see that the temperature here is quite different from the temperature on the other extreme end. This is a cold temperature. So when you heat it here, we're going to see how this heat, because it's a metal, so the heat is going to move, right? And we say that faster vibrating ions collide with the slower vibrating ions. The faster vibrating ones will collide with the slow vibrating one. That's what is happening here, because you're heating it. The ions that get heated up quickly, they vibrate and collide with the other ones, and then the heat gradually gets spread. It's spreading on this surface till it gets to the other end. Is that okay? And then the thermal energy is transferred from the hotter object to the cooler object. The thermal energy will move from the hotter side to the cooler side. This energy is going to spread to every other part. Then, like we show you, these are the electrons. The dark one that has an arrow showing that these are the electrons. And then we also told you these are the atoms. The one that have arrow on both sides that only vibrate about fixed position. These are the atoms. Okay? So when heat energy is supplied, then you see that the atoms vibrates and pass the energy from one part to the other. How? With the help of the electron. As they vibrate, the electron helps to carry the heat and give it to the next atom, and then vibrate and give it to the next atom, and like that, then the heat begins to spread. The heat energy begins to spread from the hot part to the cold part. Is that okay? Now, conduction can occur through two mechanisms. One of the mechanisms through which conduction occurs is by atomic vibration. See, these atoms will be vibrating. That's one way. By vibration. As they are vibrating, they might even be hitting each other. You know, sometimes they're very close. The atoms are very close. As they have, not just the way you see it in the diagram. For diagrammatical sake, that's why you see it like this. But in reality, these atoms are actually close. They're touching each other. They're so close to the point that they're touching each other. So they vibrate. So there are two methods by which the heat energy is being transferred in a metal. Two methods. One is by the atomic vibration. The atom is vibrating. So they vibrate, they touch each other. Then the heat this one gets, it gives to this as it touches it. The heat this next one gets, gives to this one as it touches it. The heat this one gets, gives to this as it touches it. So that's one way by which the heat energy is being transferred in a metal. Another way by which the heat energy is transferred in a metal is by free electron collision. You know the electron moves. The electrons can move. These dark ones, they can move. Okay, so they collide with themselves, they collide with the other metals. So free electron collision collide with the walls of the metal, collide with themselves. As they are moving, colliding with themselves, colliding with the walls of the metals, they are passing on the energy. They are passing on the heat energy from the hot part to the cold part. They're passing on the heat energy from the hot part to the cold part. They're passing on the heat energy from the hot part to the cold part. Okay, now let's move on quickly. We say when a substance is heated, the atoms or the ions start to move around and vibrate more. When you heat it, the atoms start to move and even vibrate more, right? So when we say when you heat a substance, a metal is heated, the atoms or the ions, they will start to move around or vibrate. Even if they don't show like movement from one place to another, they vibrate about their fixed position by passing on the energy. Okay? Then the atoms at the hotter end of the solid will vibrate more. Why? Because they've gained more kinetic energy. The atoms at the hotter part will vibrate more. They've gained more kinetic energy. They have higher temperature at this point, so they're going to like be vibrating faster because they got super hot. They got super heat thermal energy. So they will vibrate more than the ones here. These ones are very comfortable. These ones are cold regions. They vibrate a little bit, just a little bit. But the ones on the hot part, they vibrate more because they get more kinetic energy. So their speed will increase. You know, the average kinetic energy will increase the speed of the collision. So the atoms will collide even more, faster. And since speed increase, then the rate of transfer of energy will increase as well, right? So that's what we said. The atoms at the hotter part or hotter end of the solid will vibrate more than the atoms at the cooler end of the solid. Now, as they do so, then they bump into each other because they're just vibrating, the concept that we've explained already. As they vibrate, they bump more into each other. They heat themselves. They bump more onto each other. They transfer the heat energy. The one that has it, the one that's at the point of heat, we pass it to the next one, and then that one heat vibrate, pass it to the next one. This is how the process continues. The heat keeps being supplied, so you're not going to die off. As you're passing in and vibrating, more and more of it is being supplied to you. So just think, once you get it and pass it on, it doesn't have it again. Once you get it and pass it on, it doesn't have it again. No, because the heat energy comes continuously. You keep heating. So the energy you're getting in, you pass it, you receive it, you pass it, you receive it, you pass it. That's what is happening. They're getting the heat energy and they're passing it and they're getting more. So these collisions transfer the internal energy of the thermal equilibrium is achieved throughout the substance. This collision will ensure that the heat energy is passed till there's equilibrium attained. What do we mean by equilibrium? A point whereby the heat is uniform throughout the material. The heat energy is not same. Everywhere is warm. Everywhere is warm. No cold part or super hot part. The heat energy will be same everywhere in the material. When that happens, you say, the material is now at thermal equilibrium. When that happens, you say this material is at thermal equilibrium. Is that okay? Now, this occurs in all solids, metals and non-metals alike. Whether it's metal or it's non-metal, these characteristics happens in all of them. Is that okay? Now let's move on specifically to extended thermal conduction in liquid and gas for extended student, for IGCSE student. Thermal conduction in liquid and gas. Now, for thermal conduction to occur, the particles needs to be close together so that they can vibrate and the vibrations are passed along. Okay? For thermal conduction to occur, the particles needs to be close together so that they can vibrate and the vibrations are passed along from one to the other. And this does not happen easily in fluids. You know, the particles of fluids are not super close together. They're not super close together. So that's why thermal conduction is not like super happening in fluids. In liquid, particles are close. For liquid, they're close, right? The particles are close, but they slide past each other relatively. So in gases, particles are widely spread apart and will not nudge each other. So both types of fluid, whether your fluid is a liquid fluid or gas fluid, are poor conductors of heat. Both of them are poor conductors. Why? If they ask you why are fluids poor conductors of heat, whether they are liquid fluid or gaseous fluid, why are they poor conductors of heat? Because conduction requires particles to be closely packed together, so that when they vibrate, they can pass on the heat from one particle to another. But in the case of fluids, whether it's liquid fluid or gaseous fluid, the particles are, although the liquid fluids are a bit close, the particles are close, but they're not like tightly packed or like solids. And the gas, they're even further apart. It's even worse stuff in gas. So even if there is any conduction, it's a poor one. It's not a good conductor. It's not a good conduction. So we say fluids are not good conductors. They are not good conductors. Is that okay? Because reason being that the particles are not closely packed together so that they can support themselves with the help of vibration. Because conduction happens when particles vibrate, and when particles vibrate and pass on the heat energy from one particle to the other just through the process of vibration. Just through the process of vibration. The particle that gain the heat energy, the average kinetic energy, pass this energy by vibration to the next particle. They just vibrate and touch each other and pass on the heat. So that's why metals or solids are good conductors, whereas liquids and gas, they're not good conductors. Why? Because the particles are not closely packed together. They're not closely packed together. In liquid, even despite they're close, but still there's space between the particles. So they will not be good conductors even if there is at all. In fluid, in the gas, the particles are further apart. There is little or nothing taking place in terms of conduction in gases. Is that okay? So now let's move on. We've seen this part. Let's go to relative thermal conductivity. Let's take a look at some materials and see how well they conduct. How well they conduct. For still on the extended, we say conductors tends to be metals, right? Conductors tends to be metals. Like metals are very good conductors. Metals are good conductors. Why is this so? Because the better thermal conductors are those with delocalized electrons, which can easily transfer the energy. Yeah, that's why metals are good conductors. They have delocalized. If you look at what we've looked at before, we have acknowledged that the metal, if you take a look at metal, they have atoms or ions, and they also have electrons. These electrons are called the delocalized electrons. Why do we call them delocalized? Because they're able to move from one place to another to pass on the heat energy from this hot side to the cold side. They're able to move. They're very free to move. I mean the small, tiny, dark one. They are the electrons. They are called the delocalized electrons. They gain heat energy, and they're able to pass it off from the hot side to the cold side. So this only happens in metals. Okay, so that's why metals are super good conductors. Whether they're metals, solids are good conductors, but metals are better because metals they have their delocalized electrons. Okay, so they're able to pass on the heat energy from the hot side to the cold side. They're able to pass on the heat energy from the hot side to the cold side. Now, we also said this means that there is a wide range of thermal conductivity among materials. So we want to look at different materials and their different rates of conductivity. We're looking at different materials and the different rate of conductivity. Now, if you have copper, iron, carbon, water, air, glass, and rubber, we have 1, 2, 3, 4, 5, 6, 7. We have several different materials we put together. We just use diagram to illustrate these materials. And then when heat is supplied, you can see copper is a better conductor than all of this one. You see copper is a better conductor, better heat conductor than any other one is. Okay, copper is a better conductor than anyone else. And then we have iron. We have iron and next to it, which is next to copper. Then we have carbon, and then we have water a little bit, and then we have air. And then when you get it here, when you get to glass, you see glass is a poor conductor. You can see it's a poor conductor. The heat energy is not super spread to this side, and then rubber is a super poor conductor. So this is how the conductivity comparing these seven materials. Copper is number 1, iron follows, carbon follows, water follows, air, glass, and then rubber is the last one. Is that okay? So I think we stop here. right? But let's see what we have. Okay, our next one will be convection. Thank you very much for joining us.